street lighting. But first I have to clean the wall. But do anyone have a handkerchief or something, or paper?
I think.
Towel? Something like that.
No.
No.
I'm sorry.
Yes. Yeah, my dear. I don't know if this works. Well,
Ja.
Hast du praktisch? Ja, das. Sie hat einen da steht.
so actually, so you got the whole lecture on this.
Ja.
This will be part 2.
Our answer will be like this at the exam.
If you can remember that, then it's fine. So actually, the problem might be street lighting. We've got the power station, and then we got a lot of bulbs. Then we got the back conductor. That's actually ground. But this we also have in electronics. We always have a ground potential. And ground potential is actually the idea of the Earth potential. Yeah? So that's ground, that's our reference. We all the time need a reference. For your measurement, if we're doing a measurement and we say the voltage, we do not know what voltage actually is 9 volts. That means the voltage is 9 volts above ground potential. Yeah? So every measurement is always referenced to a ground potential. Ground. G and D. So, and if it's getting dark, somewhere at the power plant, there must be a switch, and someone has to turn on the light. What is then going on? Let's say we have 100 meters between each lamp. And if the electrons are now moving with a speed of centimeters per second, if we turn on the lamp, it might take a little bit time until the first bulb gets on, then it might take an hour until the next one gets on. Is that true?
No.
No, actually not. So what is wrong? Is the speed of the electrons, is this wrong, or the theory behind wrong?
No,
So
but can we calculate it? Because like if we on the switch from the beginning, but for the first pole it's earlier and the last pole it's later. Yeah, but like if we from what I studied in meters, if we fire an electron in an electron gun, like we get a speed into 6 into 10 to the power 6 meter per second, the speed of electron.
yeah. So I haven't just followed you complete, but I think you mean just the right thing. So what is actually going on is, as a model, in reality it's completely different, but as a model you can think of the electrons filling up the whole wire. Yeah? And the movement of the electrons is actually with centimeters per second. But if you put in one electron here, nearly at the same instance of time, there is another electron dropping out at the other end of the line.
Ja.
And actually what current what we understand by current is electron movement. So the last L, if we counting here, our current, then there is one electron moving across this cross section. At the same instance, when we put in one electron here. And actually this information that we put in an electron here, this is traveling with the speed of light to the other end of the wire. So it's not the same instance of time. This is
It's accelerated.
this information that we put in one electron here is conveyed with the speed of light. Yeah. So if we have 1 meter, then it takes a couple of nanoseconds until the electron gets out here. Yeah. So this is actually 1 over 300 million. Yeah. So it's not the same instance, but it's a very small amount of time. And that means if you close the switch here, the information that current is flowing is traveling with the speed of light
To the end.
along the line. So actually the lamp's going on nearly all at the same instance of time, at least for a human. Yeah? But it still takes a couple of microseconds until the last lamp will lit up. Yeah? So that's the thing you have to think about. The electron movement is very slow, but the information that current is flowing in the circuit is traveling with speed of light, nearly speed of light. Yeah, it depends on the
Connection.
on the connection and on the materials. It's actually the dielectric constant. So if you really want to know it, C equals C0 divided by the square root of epsilon r, and epsilon r is the dielectric constant.
So the speed will be in centimeter per second, exact speed.
For each electron, yeah?
1 centimeter. For
A couple of centimeters, yeah. So, since no one has ever seen an electron, so it's hard to say how fast it is moving. But from experiments, you can come up with the result that's in the area of centimeters per second. Yeah? Within solids, if you are thinking about electron tubes, then the electrons are much faster than that, in the area of 10,000 meters per second. Yeah? But if you are thinking about the solid wire, then the electrons are very slow, because in the wire you have a huge amount of electrons that are moving. Yeah? So now that we have the idea what is going on here, we can define what is actually current. Yeah? Current is actually the movement of electrons per unit of time. That means it is not only a movement, but it's reference to the unit of time, and that's the second. The movement of electrons, so how many electrons are transferred per second. That means the number of electrons. You can also say the number of electrons that you can observe at some cross section. Yeah? The number of electrons that pass per second. So let's suppose we have a current of 1 amp. How many electrons do cross these cross sections?
Again, please, I'm sorry. The question.
So we have normally in electrons a current of 1 amp, it's nothing special. So it's a medium value. Yeah? So 1 amp. So let's say we have an electric circuit. We put in a measurement instrument, a current meter or an amp meter. And it says, maybe it's one with a pointer, and it says 1 amp. So what we are interested in is how many electrons flow across this meter per second. Can we calculate this? So it's not a big current, but for electronic devices it's a medium current. So 1 amp. How many electrons pass through this amp meter? Any idea? All we need for calculation, you should know by now.
We need to know. We need to know the time, and then we can calculate the.
It's 1 second.
Yeah, 1 second.
So current,
So 1
amps
amp, 1
is
amp.
always number of electrons per second.
Yeah.
That's what we define as current. Current is the number of electrons.
So it's 1 amp, one electron.
1 electron.
1 over 1 is 1.
I think as you told that the speed of electron is about couple of centimeters per second. So we are talking about in a second too. So we have to know that in 1 centimeter how many electrons are in 1 centimeter or a couple of centimeters. So the number
Yeah,
will be
that would be possible. So, yeah. So, how can you calculate how many electrons within 1 centimeter of this wire?
We know the size of each electrons, and we know the size of our tubes or wires. So we have to multiply.
Yeah. So, what's the size of an electron?
It's
I don't know
unknown.
the exact size, but
So, we are not interested in the exact number, but an idea. Is it one electron, 10 electrons, 10 million?
I think it's one. It's 1 because it's it's in 1 second, and 1 current is number of electrons in 1 second. So 1 over 1 is 1.
Current is the number of electrons per second. Yeah?
Yeah, and the answer is 1 ampere, right? Which is a current, yeah. So 1 over 1 equal 1.
That's true. But the question is it 1 over 1?
Uh-huh.
I don't think so.
So, but we have 1 second as a given. So it should be 1. It must be 1.
So maybe I give you another equation. Easier. So there is also one equation is maybe important for that problem. Since we said that each electron carries a charge, the charge was 1.6 raised to the power of minus 19. It's the charge of 1 electron. Yeah?
Yeah.
So if we have more than 1 electron, then we have to multiply this number with the number of electrons. And let's say if we monitor the experiment for 1 second, let's say we have, this is only a thought experiment, you cannot do it in practice,
Yeah.
but let's say here there's a current of 1 amp flowing. Yeah?
Divide that by
So
that.
there are the electrons, and they drop out of the wire here. They actually don't do this, but we can think about that. Then after the experiment we have an small amount of current of electrons here. And the question is, how many electrons do we have here if there is a current of 1 amp for 1 second flowing?
I think divide that by that.
So, and this heap of electron will definitely carry some charge. The letter for charge is Q. And it's obvious, the longer the current is flowing, the bigger the heap will get. So it's maybe a tenth of a second, half a second, 2 seconds, so the heap grows. So it's actually the number of charge carriers is proportional to the current. That means the amount of charge carriers that are flowing in this times the length of our experiment, times t. So the charge we actually got here within our heap of electrons is the current times t, the time. So now you can calculate how many electrons flow through the instrument if we got a current of 1 amp. So each electron carries a charge of
1.6 times
to the minus
10.
19th. It's the Q. So how many electrons do you need to get to 1 amp?
1.6.
1 electron is carrying the charge of 1.6 times 10 to the minus 19th. How many do we need?
We divided by 1.
1 coulomb equals 1 amp times 1 second.
Yeah.
And this is a number of electrons. This is a number of electrons per second times second cancels out. So the number actually is the number of electrons that are moving in the wire if a current of 1 amp is flowing is 1 over QE. Yeah?
1.6.
So that's roughly, if we leave that, so it's roughly 10 raised to the power of 19 electron are moving through this instrument per second. Yeah? And that makes it quite clear that we cannot count each electron in the instrument. Yeah? That's not possible. You cannot count. That's billions and billions of electrons. Yeah? This is even higher than our budget deficits. Yeah?
And the number of electrons? These are the number of electrons which...
These are the number of electrons that pass through that instrument per second. Yeah, so it's a huge amount of electrons within our wire. And 1 amp is not that big. Yeah? So in the power lines you sometimes get 10,000 amps or something like that. Yeah?
So the answer is not this.
The answer is this.
It's proportional to this.
So the I will be this because...
I will not be 10 to the 19th.
Proportional.
The current will be 1 amp. But what is 1 amp? 1 amp is just a number and it doesn't say us anything. But to get the link to understand this means 1 amp means that 10 raised to the power of 19 electrons are moving in that wire. Now, if you are cutting the wire here and we do our same thought experiment, then there will be 10 raised to the power of 19 electrons dropping out of this wire per second. Yeah? That's not practical. Yeah? Because you cannot do these experiments with getting the electrons out of the wire. No, they won't get out there. But at least you have the idea what is going on in the wire. If you can see into the wire with some special instruments, you will see this huge amount of electrons passing each second. So we should have the idea of current. What is current? Yeah? So that's a huge amount of electrons moving. Yeah? And that's why they are so slow, because the amount is tremendous. So what else do we have in an electronic circuit? We have current, voltage. So that's the next quality we have to discuss. So what you knew until now is charge. Charge is just a number of electrons, or charge carriers, or protons, or whatever.